Hello, welcome to my video series of data structures. This is part 5 of module 8, the graph data structure. In this video, we will explore the Eulerian path and Eulerian circuit problem. The city of Königsberg in Prussia, now known as Kaliningrad in modern-day Russia, was once divided into 4 land masses by the Prago River. These land masses were connected by 7 bridges, which are marked by the red stars on the map to the right. Naturally, the locals become curious. Is it possible to take a walk through the city, crossing each of the 7 bridges exactly once? This intriguing question gave rise to what is now famously known as the 7 bridges of Königsberg problem, a cornerstone in the history of graph theory. The problem has many real-world applications. For instance, it plays a key role in route scheduling tasks such as street maintenance, postal delivery, and trash collection, where covering every route efficiently is essential. Beyond logistics, it also has important applications in bioinformatics, particularly in genome assembly. You can find the relevant reference in this slide. Leonhard Euler was the first to formally solve this problem in his 1736 paper, Solution of a Problem in the Geometry of Position. In his approach, Euler represented the 4 landmasses of Königsberg as nodes, and the bridges connecting them as undirected edges. Using this abstraction, the city's layout was transformed into the graph shown on the right. This elegant representation marked the first known use of nodes and edges to model a real-world scenario, and is widely regarded as the birth of graph theory. Euler didn't just solve the 7 bridges of Königsberg problem. He also generalized it to graphs with any number of nodes and edges. Specifically, let's consider the following Eulerian path problem. Given a graph, can we find a path that traverses every edge exactly once? Such a path is called a Eulerian path. Importantly, while every edge must be used exactly once, nodes can be visited multiple times. In the original Königsberg setup, the bridges could be crossed in both directions, so the corresponding graph is undirected. However, this concept can be naturally extended to directed graphs as well. In this video, we will start by examining the solution for undirected graphs, and later extend our approach to directed graphs. One key assumption we make is that the graph is connected, where all edges are part of a single connected component. Without this, it would be impossible to construct a path that visits every edge. Let's try solving the problem using a random traversal of the graph. Suppose we start at node A, and at each step, we continue along any unvisited edge, if one is available. Note that graph traversal algorithms like breadth-first search or depth-first search are not suitable here. These algorithms typically avoid revisiting nodes instead of edges, and they do not necessarily construct a valid path. Using this naive traversal approach, we might construct the following path: A to B to D to B to A to C to B. Eventually, we find ourselves stuck at node B, with no unvisited edges remaining. Specifically, all edges connected to node B, i.e. edges 1, 2, 3, 4, and 6, have already been used. However, there is still one edge CD left unvisited. Therefore, this traversal does not produce a valid Eulerian path. Although our traversal was constructed arbitrarily, analyzing why it failed reveals an important insight. We got stuck at node B because it has an odd degree. That is, an odd number of edges connected to it. Intuitively, every time a path passes through a node, it consumes two edges, one to enter and one to exit. So, if a node has an odd degree, there's no way to perfectly pair all incoming and outgoing edges. If we leave an odd degree node, we won't be able to return. If we enter it, we won't be able to leave. In this sense, odd degree nodes become troublemakers for our traversal. To construct a valid Eulerian path, we might need to limit the number of odd degree nodes present in the graph. Let's now formally prove that our intuition about odd degree nodes is correct. Specifically, limiting the number of odd degree nodes in the graph is a necessary condition for the existence of a Eulerian path. Proposition 1. If an undirected graph contains a Eulerian path, then the graph must have either 0 or exactly 2 nodes with odd degrees. To understand why, consider a graph that has a Eulerian path. Suppose that this path is not a cycle, meaning it starts and ends at different nodes. In such a path, each time it passes through an internal node, it uses two edges, one to enter, one to leave. For example, as shown in the path below, passing the red node consumes the two red edges connected with that node. So, the degrees of nodes that are included as the internal nodes of the path must be even, since their edges are consumed in pairs. However, there are two special nodes in the Eulerian path, the start node and the end node. Because the path is not a cycle, we only leave the start node and never return to it. For the same reason, we only enter the end node and never leave it. As a result, passing these nodes consumes only one edge each. For instance, in the path shown below, traversing each of the two red terminal nodes consumes only one of their respective edges, which are also marked red. Therefore, both the start and end nodes must have odd degrees, while all other nodes must have even degrees. This leads to the conclusion that a graph with a Eulerian path must have exactly two nodes of odd degree. On the other hand, consider the case where the Eulerian path forms a cycle, where the start and end nodes are the same. Such a Eulerian path is also known as a Eulerian circuit. In a Eulerian circuit, every node is both entered and exited, consuming exactly two of its associated edges. Hence, all nodes must have even degrees, and the number of odd degree nodes in the graph is 0. Taken together, if an underwriting graph contains a Eulerian path, it must have either 0 or exactly 2 nodes of odd degree. Based on this proposition, we can now conclude that it is impossible to find a Eulerian path that crosses all 7 bridges of Königsberg exactly once. This is because all 4 island areas, i.e. nodes A, B, C, and D, have odd degrees. So far, we have proven that having 0 or 2 odd degree nodes is a necessary condition for the existence of Eulerian path in an underwriting graph. However, is this condition also sufficient? In other words, if a graph has exactly 0 or 2 nodes with odd degrees, can we guarantee that a Eulerian path exists? More importantly, if a Eulerian path exists, how can we efficiently find it? Before we tackle how to find a Eulerian path, let's first reduce the problem to a simpler one, the Eulerian circuit problem. We will show that if we can solve the Eulerian circuit problem, we can easily solve the Eulerian path problem as well. Given an underwriting graph, if it has 0 odd degree nodes, any Eulerian path must form a Eulerian circuit, since all nodes have even degrees. So, if we know how to find a Eulerian circuit, we can directly find the Eulerian path. On the other hand, if the graph has 2 odd degree nodes, we transform the problem by modifying the graph as follows. We introduce a full node to the graph and connect it to each of the 2 odd degree nodes by adding one edge to each. For example, as shown in the figure on the right, the original odd degree nodes are marked in red, and the newly added full node is marked in gray. The added edges to connect them are shown as gray dashed lines. After this modification, the 2 red nodes, which were odd degree, now become even degree since we added one edge each. The full node connects to 2 nodes and also has an even degree. Now, all nodes in the modified graph have even degrees, and the number of odd degree nodes is 0. In this case, if a Eulerian path exists in the original graph, it must correspond to a Eulerian circuit in the modified graph. For example, suppose that the black path is a Eulerian path in the original graph. Then there exists a Eulerian circuit that includes the full node, as indicated by the blue arrow, in the modified graph. Thus, we solve the Eulerian circuit problem on the modified graph. Once we have found this Eulerian circuit in the modified graph, we can simply remove the full node and its associated edges to recover the original Eulerian path. As a result, by reducing the Eulerian path problem to the Eulerian circuit problem, we only need to focus on solving one problem. In the remainder of this video, we will focus on how to find a Eulerian circuit in an underwriting graph. Now, let's prove that having no odd degree nodes is not only necessary, but also a sufficient condition for the existence of a Eulerian circuit. Proposition 2. If an underwriting graph has no odd degree nodes, then the graph contains a Eulerian circuit. To begin, select an arbitrary node to start the traversal. Say node A, as shown in the figure on the right. Again, note that traversal in this context means continuously following an unvisited edge if one is available, which ensures a valid path. We begin the traversal by leaving node A, thereby consuming one of its edges. Since all nodes are even degree, node A temporarily becomes odd degree, while all other nodes remain even degree. Thus, the traversal must eventually end at node A. If the traversal visits all edges in the graph, then we have successfully found a Eulerian circuit, and the proposition is proved. However, in some cases, the initial traversal may only cover a subset of edges. Denote the traversed cycle, as well as the set of edges contained in it, as T. Also, denote the set of unvisited edges as H. For example, suppose that the first traversal forms the cycle A to B to D to B to A. In this case, the green edges represent the set T, and the remaining black edges represent the set H. Recall that the Eulerian path and circuit problems are only well defined on connected graphs, where all edges in the graph are in the same connected component. Because of this, if there are still unvisited edges remaining, there must exist at least one such edge, denoted as E, that connects to a node W which has been visited during the initial traversal. Otherwise, the previously traversed path T would be disconnected from the remaining unvisited edges H, making it impossible to reach all edges of the graph. In our example, the unvisited edge E could be the purple edge shown in the figure on the right, and the previously visited node W could correspond to node B. Now, let's remove the set of traversed edges T from the graph. Because T forms a cycle, it must consume an even number of edges from each node it touches, one for entering and one for exiting. Because all nodes in the original graph had even degrees, removing edges in T still leaves them with even degrees. Thus, after removing T, all remaining nodes in the graph continue to have even degrees. Next, we continue our traversal on the remaining graph, starting from node W by following the unvisited edge E. In the example shown on the right, we leave node B using the purple edge BC. Since all nodes in the remaining graph still have even degrees, this new traversal must also form a cycle, eventually returning to node B. Let's say the second traversal corresponds to the purple cycle highlighted in the graph. Because node W, or node B in our example, is shared by both the first and the second traversals, we can splice the second cycle into the first one at the shared node B. For example, splicing the second cycle B to C to A to B into the first cycle A to B to D to B to A at node B results in a new combined cycle A to B to C to A to B to D to B to A. This combined cycle now includes all edges from both traversals, forming a larger partial Eulerian circuit. It is important to know that each new traversal consumes at least one previously unvisited edge, such as edge BC in our example. By repeating this process, we continue discovering and splicing new cycles into the existing path, progressively consuming more unvisited edges. Since we only traverse unvisited edges, and each step consumes at least one, this process must eventually visit all edges in the graph. Thus, the final combined cycle forms a Eulerian circuit that includes every edge exactly once. This proves that if an undirected graph contains no odd-degree nodes, we can indeed construct a Eulerian circuit, confirming our proposition. Back to our example, the third traversal could begin at node C and generate the path C to D to E to C, which will be spliced in the existing partial Eulerian circuit. By combining all three traversals, we construct the full cycle A to B to C to D to E to C to A to B to D to B to A. To help visualize the process, we mark the edges in this cycle with different colors, indicating which traversal each edge originated from. You can verify that this final cycle visits every edge in the graph exactly once, without repetition. We can now derive an algorithm for finding a Eulerian circuit directly from the proof of proposition 2. The pseudocode for this algorithm is summarized below. In line 2, we initialize the partial Eulerian circuit P as an empty set and place all edges into the unvisited edge set H. In line 3, we use a while loop to iteratively traverse the graph until all edges have been visited. In line 4, we select an arbitrary node V that has at least one unvisited edge E connected to it. In line 6, we start a traversal of the graph by leaving node V using edge E. This traversal will eventually return to V, forming a cycle, which we record as T. In line 7, we splice the new cycle T into the partial Eulerian circuit P. In line 8, we remove all traversed edges in T from the unvisited edge set H. Finally, in line 10, once all edges have been visited, we return the complete Eulerian circuit P. Because a Eulerian circuit requires visiting each edge exactly once, the time complexity of our algorithm is OE, where E is the number of edges in the graph. It is also worth noting that, although the algorithm directly solved the Eulerian circuit problem, it can be easily adapted to solve the Eulerian path problem as well. As discussed earlier, this is done by introducing a temporary full node connected to the two odd-degree nodes in the original graph. Finally, let's extend our solution to directed graphs. While a directed path passes through a node, it consumes one incoming edge and one outgoing edge. In other words, the traversal reduces both the in-degree and out-degree of the node by 1. This means that for any internal node in a directed Eulerian path, its in-degree must equal to its out-degree. With this observation, we can restate our two key propositions for directed graphs. Proposition 1. If a directed graph contains a Eulerian path, all nodes must have equal in degree and out degree, except for one start node, which has one more out degree, and one end node, which has one more in degree. Proposition 2. If all nodes in the directed graph have equal in degree and out degree, then the graph contains a Eulerian circuit. The algorithm for finding a Eulerian circuit in a directed graph is essentially the same as in the undirected case. The only difference is that during traversal, we must respect the direction of each edge. This concludes our discussion of the Eulerian path and Eulerian circuit problems, both in undirected and directed graphs. Thank you for watching, and see you next time.